So first of all, Aline, I would never stop thanking you for the help you gave us for the wheel walking. That was not a minor contribution, as you put it. It was a very important contribution, at least in terms of technological terms. Okay, let's do something about this presentation. So it's a very brief presentation, and I'm trying to provide the status of what we're doing in ESA and what we're also preparing in the European community. Because as a matter of fact, also the EC has a fairly sizable program in the space technology, and they also have ambitions to enter into supporting or even making space missions on their own. So let's go to the contribution of ESA. So I'll try to work first on shortest distance. What happens in terms of exploration of the moon? Well, at the moment, really nothing. We are contributing, of course, to the gateway. However, in the gateway, there is the intention to have the possibility to control assets on the moon from the gateway. So this is where we have been working ourselves at ESA, but also with the help of DLR in trying to understand what is the soft spot between advanced teleoperation and also autonomy that can be implemented into the robot system. In fact, it's been a very beautiful collaboration. We've been working on the part related to teleoperation. You see here, we have run an experiment in which we brought a standard force feedback system, I mean, state of the art that is available in Europe, which is also the state of the art worldwide. And we qualified for space use and brought it to the space station. And in this context, you see an ESA astronaut that is operating the arm. And at the same time, we allowed the operator to work on a mock lunar scenario for which we have prepared a Rover system, which was there to essentially pick up samples. Our astronaut was, first of all, trained in geology, and essentially he had to go around in this very large area. This was an industrial hangar. Actually, it was an aviation hangar, which we had equipped with some sampling sites. And what we did was essentially letting the astronaut go around and look for stones that were particularly interested to be collected. So this worked very well. Similarly, with the experiment done by DLR, and I think Aline has just very briefly touched the subway adjusting experiment, the subway adjusting system was a task to operate on a mock power solar station and from the space station, and also this one worked like a charm. The interface was actually this tablet that you see on the right part, which was uploaded by ESA, but it was equipped with a smart user interface made by DLR, and this was really a context-based interface. So the astronaut would just point on objects, and the system would provide the type of actions the robot could undertake on those specific objects. A very, very good way of working, not only in terms of operating the robot, but also in terms of collaboration between agencies. Next, well, we do have actually missions on the moon that are developing more advanced in terms of TRL. So at the moment we are building up the Prospect payload, which is something that we are contributing to the Russian exploration of the moon, which will have the Lunar Resource Lander in 2025. And our Prospect system is essentially made of two parts. One is a drill led by the Leonardo company in Italy. And this is a derivative of our development for the ExoMars drill. It's a derivative in the sense that some of the qualification steps, the technology that for the drives is very similar, but it's a drill that is also on some elements simpler because it's a single stem, so it does not have this complex mechanism of assembling the drill string out of drill pipes. So there is a single drill pipe. However, it has a very demanding situation because it has to drill by controlling the temperature of the drill bit very carefully. Why do we go in this particular mission? Because we would like to sample the icy volatiles. Now, the temperature of these icy volatiles is very low, but it takes really few degrees to make the volatiles turn from from ice into gas, and so disappear. So drilling in these conditions requires a very careful control of the energy that the drill system is imparting on the soil. The other part is the sample analysis package. Okay, this is a bit less relevant, but the system has in any way, the drill has to provide things that are suitable not only for our own package, but also for the lunar Russian package. We are in pretty advanced stage in the sense that everything has been tested functionally, so under extremely low temperature and a very low pressure in icy lunar regolith. So we have a demonstration that this type of operation can be done. Next one. So we move further away. It's Mars. Now, ExoMars is, I guess, known. It's a mission that intends to look for traces of life, whether extinct or extant. The robot system is a very complex one. Also, it has many complexities related to the way the investigation is carried out. Let me explain how it works. I have a next slide. So the rover itself is equipped on the front part of this black box that you see here of a drill I was mentioning before. It's a multi-stand drill. And the drill can rotate and can, of course, drill up to 2 meters in depth. Why 2 meters? Because we believe that any trace of life on Mars has essentially been obliterated and almost made invisible on the surface by the radiation accumulated during many years. So you see again the arm. The drill. The driller will put the samples into this tiny window where there will be a tray coming off. How do we select the area where we want to drill? Well, there is back on the back side here, this GPR, this radar, ground penetrating radar, which is used whenever, by means of the detection system, so by the panoramic camera, we can select rocks that appear to be bedrock. The interior part is what made the system very, very difficult. You see, in order to detect extremely faint traces of biological elements, you need to have a system that is clean. It's actually, ExoMars is probably the cleanest thing there is on Earth at the moment, because we had to clean it to an extent that there wouldn't be any trace of spores or any other biological element within the rover. Otherwise, we would have the effect that thanks to the sensitivity of the instruments that are in ExoMars, you do not detect what is of Mars, but actually you are detecting what you're bringing from Earth. So the cleanliness was the thing that complicated enormously the thing, made the assembly operation extremely complicated because everything had to be clean completely. You see, in biological terms, the principal polluter of a system that needs to be clean is actually the human being. So assembling something with humans and keeping it also very clean has been a major hurdle. Now, the system itself, as you see, is full of components. Rover systems for space are exceptionally complicated because essentially they are themselves a spaceship, completely independent and capable of carrying things on their own. Now, about the locomotion system, Alan was mentioning the wheel walking. As you see, the rover has 6 wheels, and these wheels have the ability to swing back and forth. And this allows them to essentially work very well in situations where the soil is not very consolidated, so the wheels tend to dig down. It's been demonstrated and shown very well, and you have seen the video of Aline, that actually by swinging the wheels back and forth, and so limiting the pressure on a wheel that is moving forward, we can avoid important digging of the wheels, and so we can actually decrease the slippage that the system sees. So basically, with this wheel walking system, we managed to grow the capability of the rover of about 5 degrees with respect to of what we will be doing in a situation where the soil and the slope are not very favorable. What do we do with ExoMars? Okay, it depends when we launch. Hopefully this will be in 2 years from now, if COVID does not bring a further complication, but we have already started to work on the next system. The next system is in support of the NASA sample return mission. With the experience we made in ExoMars, we have essentially developed sufficient skills to make a rover. And this is another rover, and this is our contribution, together some others. I will be talking about the next one. So this is a sample fetching rover. And it's, unlike ExoMars, is a 4-wheel system. The 4 wheels are essentially due to the extreme packing factor that this rover needs to have. You see a picture here contributed. It's one of the early models of the lander. So the rover will be sitting and essentially on top of the lander and packed in the end cone of the descent module. And this is, you see on the right, the packing situation. So the wheels are all folded around, and these are the 2 stages that you have until the things essentially unpack. What are the objectives of this rover? Well, essentially it is meant to go from the place where the JPL lander lands and to the places where the tubes where the Mars 2020 mission has left samples. So what happens in this mission that is currently traveling to Mars is that you will get these samples being delivered, collected by the rover, and also left into some sample caches, essentially just put on the Martian soil, waiting to be collected by this particular rover. So the mission of this rover is to traverse from the landing spot, detect and pick up the tubes, and this will be done by a robot arm, storing the tubes and then returning to the lander. So this is done with the rover that is sensibly smaller than ExoMars, 230 kilograms. It has also a much higher speed. We're going for 200 meters sol average. And it's also targeted for a 4 kilometers total traverse. But of course, with margin, this will be a lot more. It is solar power. There will not be any radiation-based system, either for thermal control or even for power. And it has the capability of store up to 30 tubes. And I'm going to show you a little animation that was prepared by our animation guys, so you can imagine how the rover runs. So it has a dual bogie with the differential suspension. It has deformable wheels that are actually contributed by NASA. And it has a front arm, which allows it to essentially collect the samples that, as you see, are left on the soil. And essentially it goes in a completely autonomous way from one sample to another. Also because the mission will be fairly short, so there is no time to have a ground loop in order to instruct the rover to be able to pick up an individual sample. So once the location of the cache is defined, the rover should be able to pick up all the samples independently. Another contribution we are having, which is also robotics, is the sample transfer arm. So when the sample fetching rover returns to the lander, there will be a second system, which is a robot arm placed provisionally. You see it here under another model of the JPL lander, which is in continuous evolution. So you see different pictures in different times. So what happens is that this robot arm, which is also made by the Leonardo company, for which we have already designed several technological specimens. We have a complete set of robot drives that have been qualified, although for a different size, but I mean, the recipe is very much the same. So this is at the moment in the conceptual form is a 7 degrees of freedom manipulator. And it has, I don't know what, it has 2.2 meter full extension, about 37 kilogram, considering all the 20% margin that is due at this stage of the development, 40 watt to 75 watt peak power. And the idea is to have the joint electronics integrated on each joint. And this is done in order to minimize the number of cables that are running through the robot arm, and also to be able to implement the force loops in a very close proximity to the sensors that otherwise would be subject to noise. So here is what has been done for the sample return mission, but we are working also for future missions. And you should know that we work together also with the European Union in an activity which is called the Peraspera. This is an activity in which ESA, together with the Italian Space Agency, the Spanish one, the French, German, UK, and the Polish, somehow it's ended up on the right of this form. We're cooperating and creating this roadmap of things that we believe will happen in the future. The roadmap is made of an orbital part, but what is relevant to this workshop is, of course, the planetary track. So within this roadmap, which is harmonized across all these agencies, so what we do at ESA is also reflecting this particular roadmap. We are looking at the three time horizons. So essentially a short-term to medium-term one, a mid-term to long-term, and finally a very long-term one. And for this, we're looking at long-term autonomy for the short to mid-term. So how to grow up in extended missions that are targeting more distance being done into the Martian or the lunar surface. We're targeting as well a deeper exploration. For example, at ESA, we are developing a 20 meters drill, which would be something that is a radical departure from the ExoMars drill and from the lunar drill. We'll use some other technology. And so we are doing for extended mission. And instead, in the mid to long term, we're looking at the difficult sides. Alan has already presented this idea of going to craters and to caves, and this is where we need this capability. And finally, in the very long term, we think that the exploration will not be limited to just exploring, but also taking the resources that are in space in order to aid the exploration, but also some form of exploitation. So what is happening right now at the level of DC is that we have a few activities running. For example, we've been working at the moment with this ADE project, autonomous decision making in very long traverse. The scenario is depicted in this pictures. So essentially travel independently from a starting point, avoiding obstacles. Nothing special about this. It's done, of course, now. But when we are targeting kilometers, well, then all the technologies that are taken nowadays, especially with respect to localization, start to be not adequate, because you cannot go anymore in terms with the local localization. So dead reckoning, you need to understand the global localization. You need to implement the global localization. And when you do also this very long traverses, you end up having the possibility of doing some opportunistic science, which the system is endowed to do. And finally, you must be able to detect things that are for collection, being, for example, the sample caches, but also once you have done this opportunistic science, you maybe want to bring samples of what you have identified as interesting. So this is the ADE project, which is running right now, and it will be finishing in the course of next year with a rather hopefully spectacular demonstration done in the Tenerife Islands, if COVID allows it. The next part is related to robotized construction, which is the far in time scenario. And it is speculating on the fact that whenever you will have something that requires building, construction, extraction, and so on, you will have teams of robots. So ProAct is the name of the project that deals on the fundamental autonomy element of heterogeneous robots that need to cooperate with a common goal. Why heterogeneous? Because we will not have the possibility of working with just one type of robot. There will need to be robots that have different abilities. In particular, in ProAct, they're using a walking robot, very capable with arms, and a traditional wheeled rovers, and also much less capable robots like a gantry that is only meant to transport heavy stuff or use it to make a 3D printing of the structures. And so this scenario targets the collaboration between these three elements in order to achieve the mission, which is building a structure on a lunar scenario. Finally, in the call 2020 is already is being awarded at the moment. So I cannot give you details of what is happening because unfortunately this is still covered by the negotiation procedure. The only thing I can say that we have selected a team that will take care of lunar cave exploration by cooperating robots. And the grant should be starting very soon. And probably you will hear about this. Okay, so conclusions very simple. We have a number of planetary missions that are being prepared. We want to reuse every time everything we do. So ExoMars is being used to capitalize, as you see, both on the lunar missions and on the future space mission, Mars missions. We are also capitalizing with the links we have with the European Union and with the other agencies in order to make sure that the contributions at European levels are very well harmonized. I think I finished my talk.